Good morning to all. Let me resume the online classes in a molecular spectroscopy. We have already compute the rotational frequency. V rotational is equal to S divided by 4 pi square I under Jj plus 1, where J is my rotational quantum number and I is moment of inertia for a rigid rotator. We have assumed that for a rigid rotator, and this derivation, this result we have achieved with the help of utilizing our quantum mechanical description of the rigid rotator, two molecule, diatomic molecules. Now, once we have to investigate the energy of this rigid rotator in terms of the wave number, then simply what we need to define that total energy have to be divided with the help of h of c. Then f of j is equal to E upon hc. This angular bracket doesn't mean that any kind of the expectation value over here, and it's simply a f, which is a energy in a wave number for the rotational energy. So now the rotational energy we have achieved, that is h upon 8 pi square IC jj plus 1 centimeter inverse. And now in place of this h upon, because these all are the constants, then putting this h divided by 8 pi square I of c is equal to b, known as the rotational constant. Then simply we got this fj is equal to bjj plus of 1 and 6 centimeter inverse, where j is equal to 0, 1, 2. So once you are putting the value of j, these are all the positive real numbers, then this fj is equal to 0, 2b, 6b, and 12b, 20b, and 30b. So we have this series of discrete rotational energy levels where spacing increases with increasing quantum number j. So if the transition is taking place from upper level j prime to the lower level j double prime, where this j double prime is less than to j prime, the wave number of an emitted or the edge of the rotation would be given by simply this nu is equal to fj prime minus fj double prime. Then you have this vj prime j prime plus of 1 minus vj double prime j plus of 1. So the study of a matrix elements of a dipole moment shows that the rotational transitions can only occur such that j changes by unity, that the selection rules as delta j is equal to plus minus of 1. So putting that j prime is equal to j double prime plus of 1, and putting this value in this relation, then we have this frequency nu is called rotational frequency. What we got this wave in term of wave number is equal to 2bj double prime plus of 1. In this formula, the j values of only the lower state occurs. That this we may write j for j double prime for simplicity by removing these primes from this relation. Then simply we could represent this nu is equal to 2bj plus of 1, and substituting again this j is equal to 0, 1, 2, then nu is equal to 2b, 4b, 6b, and 8b. These are the difference between these quantized energy labels. If you plot these quantized energy labels in this fashion, where this is ground level, then first excited state, second excited state, and so on. So the difference between these energy levels is 2b, 4b, 6b, 8b, and 10b. These are the difference of the frequencies or the energies. The absorption spectra of a rigid rotator is expected to consist of a series of equidistant linear with constant separation, that is the 2b, provided the transitions starting from a various energy levels j 0, 1, 2, 3, and so on. But you remember that the delta j is equal to plus minus of 1. However, does take place because a good number of rotational energy levels are well populated even at the ordinary temperature. If you have to calculate the population in a level of jth level, so from the partition function, we could write that this the number of atoms in the jth level divided by total number of the atoms is equal to 2j plus of 1 e minus exponential of minus ej minus e naught divided by of k of t, and this n j divided by n naught is equal to 2j plus 1 of exponential of this quantity. So this where this 2j plus 1 is coming, because we are taking the degeneracy into account. Then for a even this thing we have done in this, once we did our angular momentum problems, then there also we have counted that the how this degeneracy take place. So this 2j plus 1 is coming for the degeneracy case. So for this relation, once you will calculate, then you will be getting a simple this spectra corresponding to z, you will be getting that maximum at somewhere here. And or what we could do, simply you just take a first derivative of nj with respect to z, and for the maximum value of this one, just to make it 0, then you will be getting that the value of j is equal to, it is not mentioned over here, then j is equal to under root k of t divided by 2bhc minus 1 upon 2. If the value of j is approximately under root kt divided by 2bhc, both the quantities are in under root minus 1 upon 2, approximately that value will be providing the maximum population in a state of jth state. So it means that if you look at the room temperature itself, we have sufficiently populated atoms, rotational states in a jth, for a jth quantum number. So for example, for a diatomic molecule HF, which shows a series of approximately equidistant absorption maximas, these are the spectrum levels. The mean spacing is found to be the 40.5 centimeter inverse. Experimentally, it was achieved that this 2b is equal to 40.5 centimeter inverse. From there, once you have this 2b quantity, then you can estimate, because b you have everything. From the b, you can estimate the value of v, you know that is h upon 8 pi square I of c. Then once you have the value of 2b, then you can estimate this mass, you know, the atomic mass, you know, then intermolecular distance you can estimate. From there, you can estimate, which is this 0.937 angstrom, which is fairly agrees with the value obtained from the other techniques. So spectroscopy itself a very strong technique to diagnose, to measure these intermolecular distances. So this is all about the rotational spectroscopy. Now, what we presume that the diatomic molecule behaves like a rigid rotator. In practical, this approach, again, I'm emphasizing over here. I said that these are the approximation, rigorous approximation. Practically, it is not possible to have a diatomic molecule behaving like a rigid rotator. So, in practical, now let me deal about the non-rigid rotators. The non-rigid rotators, because this molecule, the atom itself are vibrating at their respective places, so there is a bond stretching and the sinking. So we cannot consider it as a absolutely rigid rotator. So then it was estimated that there is some modifications in this rotational energy levels. Rather than this fj is equal to vjj plus 1 minus, you have the another constant is d, where this d is called the centrifugal distortion constant, and it is much smaller than this b. The value of d is not mentioned over here. The value of d exactly equal to, in term of the b, this d is equal to 4b cube divided by nu square, nu bar square, where nu bar square is a fundamental vibrational frequency of the atom. Means that the atom is vibrating with the frequency of nu bar, then this is the fundamental frequency of the vibrational frequency. So in terms of the fundamental frequency, fundamental vibrational frequency, this D is estimated is equal to 4B cubed divided by nu bar square. Due to this centrifugal term, as we are increasing the value of this Z, the spacing of this energy levels is reducing. So in this figure, if you look at here, you have a rigid rotator, and the right hand side is a non-rigid rotator. If as you increasing the value of J, the spacing gradually decreasing. It means that for a higher level of the rotational energy levels, the energy between the two successive levels is reducing sufficiently. So it was observed experimentally that for the lower value of J, this approximation is good enough, but we are going for the higher level of the J, this approximation is not fair enough. So then this centrifugal distortion constant has been introduced to estimate proper energy levels, to estimate the proper energy levels. So now again, if there is a transition between the two levels, then this nu is equal to fz plus 1 minus 2 f of z. Now just putting this value in this relation, now in place of this z, you have a z plus 1, and in place of lower energy level, just add z. Now you need to incorporate this d itself. Then finally, once you will be just a simple algebra, then you are ending up with a relation that this rotational frequency, energy, this nu is equal to 2bj plus 1 minus 4 of dj plus 1 of the q. This shows that the separation between lines decreases slightly with increasing the j, because as d is very less than to the b. Because once the z is very high, then this quantity will be sufficiently high. As this is very lower value, then because this d is very small as compared to this b, then this is negligible for the lower energy levels. Now this is the rigid rotator and the non-rigid rotators. Now another effect, that is the isotope effect. Now if you have a molecule having the different isotopes, so once you are estimating its rotational spectra, again because you have the reduced mass mu, where this constant b you are putting is called h upon 8 pi square mu r square c. This mu, if it is changing, there must be change in your b. If change in the b, then there must be change in a energy levels. So what happening that for the electronic one, for a electronic effect are negligible as their mass is very small. However, for a certain molecule, any atom, the maximum mass is concentrated at the nucleus. So the electronic effect won't be influencing much, and we are ignoring it. So this mass is generally, we are talking about the nucleus. So once you have a nucleus mass change, that is all my isotopes. So then if Bi be the rotational constant for a heavier isotope, then this Bi will be less than to B, because what happening that this mu reduced mass is a denominator. So that is why if the mass is increasing, then the B must be less. So simply I could correlate this Fi of J will be less than to Fj. So simply in the same way, what we have a non-rigid rotator, simply once you are plotting the energy diagrams, then the separation will be decreasing for the isotope. If the mass is reduced to 1, less 1, then you have energy separation will be higher. So thus the separation of levels for the heavier isotope will be smaller than thus of the corresponding levels of the lighter isotope. Hence the spectral lines will be also closer. So this is all about this rotational spectra, isotope effect, rigid rotator and the non-rigid rotator. Thank you.